Alcohols and ethers are some of the compounds that can be prepared via substitution reactions. So if we start with a hydroxide and an alkyl halide, we could simply do an SN2 reaction to get the alcohol. And if we start with a methoxide and an alkyl halide, we could again do an SN2 reaction to get the ether. This type of reaction is called the Williamson ether synthesis. So from now on, you're going to start seeing so many new reactions that the best way to study for it is to prepare flashcards. In the front, you can put the title of the question, sorry, not the question, the reaction, and the overall reaction. And then in the back, you could draw the mechanism of that particular reaction. So this is a practice that is very common in organic chemistry because there are so many reactions with many different mechanisms. So if we talk about the Williamson ether synthesis, this reaction can happen in two ways. We either start with the ethoxide on this side and then we have a secondary alkyl halide, or we can have a primary alkyl halide and this is our ethoxide. This one is the preferred path because you see we go through a primary alkyl halide, and you know primary alkyl halides will react faster in an SN2 fashion. Now, how do you get an alkoxide? So to get an alkoxide, that is exactly what you need for ether synthesis, what we usually use is sodium hydride. It's very convenient because sodium hydride will, the hydride will come, get the hydrogen, and then that will give us sodium ethoxide. That is exactly what we're going to need for this Williamson ether synthesis. And then the side product is going to be H2, which is a gas, and it just bubbles through the reaction mixture. And then we will often use this reaction to form epoxides. So when we have a halohydrin, what it means is that you have an OH and a halogen, and they are in adjacent carbons, just like this one. And so what you can do is basically an internal SN2 reaction in which you have a base. Imagine we use the base that we just talked about, is sodium hydroxide. That will get the hydrogen. It will form the ethoxide in this case, or and then the minus will go and attack my electrophile. Remember that this has delta plus and this has delta minus, and so that can attack that carbon, displacing the leaving group, and that will form this three-member ring epoxide. You know that OH minus is not a good leaving group, but as I mentioned, what you can do to overcome that is to transform that OH minus into water by using acid, and then the nucleophile can come and attack. So nucleophiles here can come and attack that electrophile, and the leaving group will be a halogen, and so that's a good leaving group. But then if the nucleophile comes and attacks, then OH minus is not a good leaving group because it will simply come back and attack again, right? So that's not a good leaving group. So in order for these reactions to go whenever we have alcohols, we must convert the OH minus into a good leaving group. And in this chapter, we're going to see different ways of converting OH into a good leaving group. So here is the example that we talked about the other day in elimination reactions. So the alcohols they will get protonated with a strong acid, and then the leaving group in the strong acid will leave, right? In this case, we have Cl. In the case of if we have an hydronium, the part that will leave will simply be water, right? And so at that point, we have water that it's a really good leaving group. Ethers undergo less reactions than alcohols, but one particular case of ethers, the epoxides, undergo one particular type of reaction. In this case, the O minus will open up, and that will be our leaving group in a way. And that is because the three-member ring is very strained, so it wants to open up and it will relieve some of that angle strain because it's a three-member ring.